So in question 1, you're given a boundary value problem, which, remember, a boundary value problem has two pieces. It consists of a partial differential equation, which is this piece right here, that relates the solution function, which in this case is called u, relates its partial derivatives together. So this is the partial differential equation part of it. But then the other part of a boundary value problem are the boundary conditions. And so that's what's provided here. And this is sort of a general comment that is something that applies to both this problem and the second problem. That in order to be a solution of this boundary value problem, a function must satisfy both the partial differential equation and the boundary conditions. So this whole thing together is a BVP. On the front side of the page, what I've asked you to do is kind of go back through the steps that we used in class to discover the general form of a solution to the vibrating string equation, which looks sort of like this, except it has a second derivative with respect to time on the left-hand side. To go back through that process and derive the general form of the solution for this boundary value problem, which relates to heat transfer, the so-called heat equation. And so I feel like most people sort of felt their way through that process either on their own, or some of you, it was obvious to me when I was reading it, consulted with another source, something that's out in a textbook. This is more or less a standard derivation, more or less a standard set of steps, which is the same set of steps that we took in class to arriving at the general solution. If you do consult another source to find something like this, I'm going to be looking in your writing for something that indicates that you understand what those steps are and what they mean. So if something appears out of nowhere, I'd like to see some explanation alongside it. So if that was you, and if I asked you to revise your work based on that, just make sure that you add some annotations in there that show me that you understand what's going on in those steps, because otherwise it's not really the point of this exercise. But where I really wanted to direct some attention is I'd like to see most of you that I assigned revisions think more closely about the second part of this problem. In the second part of this problem, scroll down to it here, the original boundary conditions in the first part of the problem were boundary conditions on the value of the function u. It was u of 0 comma t is equal to 0, and u of L comma t is equal to 0. So that was the original. And this corresponds to a problem where I have some bar or some medium that actually transfers heat, and at one end of this bar, the temperature is equal to 0. So it's being held at some absolute 0 temperature at the left end, also being held at some absolute 0 temperature on the right end. So that's the original set of boundary conditions, which physically is a really hard thing to do, right, in practice. If you know about sort of thermal physics at all, cooling a body down to absolute 0 is a very, very difficult, prohibitively difficult thing to do. It just doesn't happen. We can get really close, but we can't actually get all the way there. So this isn't actually probably a very good model for most of the heat transfer problems that we might be concerned about if we're sort of applied mathematicians or if we're working in physics. So it's actually much more easy to physically realize the second set of boundary conditions. And in the second set of boundary conditions, rather than corresponding to a heat distribution or a heat profile in which the temperature is equal to 0 at the left end and 0 at the right end, right, so maybe an example of a heat distribution would look like this for the original problem, that the temperature is equal to 0 at both ends. Instead, in the modified problem, we change the boundary conditions so that the x partial derivative is equal to 0 at both ends. So I want to just quickly point out what that represents, and then hopefully give you a little bit of a hint about how to use that information to rethink the work that happened in the first part of the problem. So first of all, what does it mean if I'm looking at the graph of a function? If I say that the x derivative is equal to 0 at both endpoints, what kind of a shape does that graph take? Or what does that tell us about the shape of the graph? What's the x partial derivative look like? Or maybe I should just make this a one-dimensional question. What does the derivative with respect to x tell you about the shape of the graph of a function? Well, it looks like our original graph might have looked like a sine curve, right? This kind of has like a sine-like flavor. right? If you did the derivation in the first part of the problem using the original boundary conditions, you probably found that the sine function described the spatial distribution. It described the building blocks of the separated solutions of the original boundary value problem. And the reason sine gets away with doing that is that the sine function is equal to 0. Its value is equal to 0 at both the left and the right ends of each half period, right? So what changes if instead of insisting on the value being 0, we insist on the derivative being 0? Why? Right. So what we're doing when we're insisting that the derivative is 0 is we're saying the heat distribution at both the left and right endpoints is not necessarily equal to 0. The temperature is not 0, but the temperature gradient is equal to 0. In other words, the tangent line, if you like, the tangent line to the graph at both the left end and the right end is horizontal. So that picture might look something like this. At the left-hand endpoint, we have a horizontal tangent at x equals 0. And at the right-hand endpoint, we also have some horizontal tangent, which doesn't necessarily have to be the same. In practice, it might be. But, right? We just want the heat distribution at the left end and the right end to have horizontal tangents, not to be equal to 0, but to have a slope equal to 0. So physically, what that corresponds to is that we've taken this bar and we've insulated it at the left and the right ends. The reason that we can say that we've insulated it is that according to the heat equation, the partial differential equation we're working with in this problem, heat moves, so thermal energy moves from one point in space to another point in space because there is a gradient, because there is a either increasing or decreasing with respect to space distribution of heat. If I have more heat on the left than I have on the right, then the heat is going to try to move from the left to the right and even itself out, right? And vice versa. If there's more heat on the right side than there is on the left, if the temperature is higher, then that also tends to try to even itself out. It's when the heat is not increasing and not decreasing with respect to space, in other words, when we have a horizontal tangent, that there is no heat flow at that point. There's no thermal pressure moving heat either to the left or to the right across that boundary. So what we would say in a situation where the derivative with respect to x is equal to 0 on both ends is that we've insulated both sides of the bar, so that no heat flows into or out of the bar from either end. So that's the physical meaning behind this. But we can see, based on Patrick's suggestion, that it looks like insisting upon that boundary condition will switch our spatial distribution of our solution from something that looks like sines to something that takes the shape of cosines. So, and I made this remark on a lot of your papers, all that I'm really looking for you to do here is to look back at the work that you did in the first part of the page and figure out where and why sines might have changed out for cosines. When you imposed the boundary conditions in the original problem, what changes in the situation where the boundary conditions now relate to the derivative instead of relate to the original function? So just looking back at the work you did that gave you sines in the first place and rethinking that particular step should show you where something that looks like cosine will pop out instead. What I'm really looking for on question 2 is I've given you actually what amounts to 2 different boundary value problems. Equation 1, which is up here on the top, and equation 2, which is in the middle of the page. On Wednesday, it was pointed out, and thank you once again for pointing this out to me, that this boundary condition that's a part of this first boundary value problem really doesn't actually work with the 2 proposed solutions that are given to you here. So my recommendation is that you just cross it out and don't worry about it for the first part of this problem, and just focus on the PDE, on the partial differential equation. Now here's where I would like to make a slight change in wording that hopefully will help you to understand what the task is here. What I've asked you to do is to show that y1 and y2, these 2 functions, are solutions to this boundary value problem, or really now just this partial differential equation. And what some of you did is try to go all the way back and try to solve this partial differential equation again, separating solutions, plugging them in, and solving arbitrarily, finding the building blocks, arbitrary constants, all that same stuff that you did on the front side of the page. That's not really what I'm looking for here. And moreover, it might not even work the same way because of this equation being different than the one that we tackled in class. So maybe what I'd like to do is just change the word show And if this makes it clearer, change it to verify. So rather than discovering the solutions of this PDE from scratch, what I'd like for you to do is just take these solutions that I've proposed for you and just verify, just plug them in to this partial differential equation and see that they work, right? I'm sort of making a claim that they work. You just have to verify that claim. But then the same is also true about what you'll do with the sum of these two solutions. When you add these two functions together, even though the original y1 and y2 solve this PDE, their sum, I'd like you to show, does not. Many of you are able to do that, but if you didn't, then that's the task that's ahead of you. What happened with some of you, a good number of you actually, when you were working on this problem, is that you keyed in on the boundary condition and neglected the partial differential equation part of this. So I saw a lot of you sort of plugging in x equals 0 and then trying to make some argument just by plugging in x equals 0 that something was true. Well, that's not enough, right? A boundary value problem has not just boundary conditions, but also a partial differential equation, and particularly now, after we take that boundary condition away, all we have to work with is this PDE. So plug these functions back into the PDE and verify that they work, but that their sum doesn't.
So you want us to take the second derivative of each one and then plug them?
Yes, right. So take each one, take its second derivative with respect to the time variable, second partial with respect to the time variable, its second partial with respect to the space variable x, and then verify that those second derivatives satisfy this relationship, that the second time derivative is equal to a squared times the second space derivative plus 1 for each of the original functions y1 and y2.
But then the a squared and plus 1 are not affected because they're constant.
That's right. So the derivatives that you're taking are the derivatives of these functions, assuming that a is a constant. Right? And then just plugging them into this equation where the derivatives are and verifying that they work. And the same comment is also true about the second part of this page, except here I haven't asked you to cross out the boundary conditions. It turns out the boundary conditions are quite important on this second part, because many of you were more successful on this portion of the problem than on the first portion of the problem. Particularly those of you who are really focusing in on the boundary conditions were more successful on this part than on the first part, because you'll probably notice that the boundary conditions are what fail to be satisfied by 6y1 on this portion of the problem, even though 6y1 still satisfies the partial differential equation. So here, the PDE is still satisfied by a scalar multiple of y, but the boundary conditions are no longer satisfied by that scalar multiple of y. Whereas earlier up on the page, we didn't have a boundary condition, and so it'll turn out to be the partial differential equation that's not satisfied by the sum of two functions, even though the original pieces do satisfy it. So the real meta question I'm trying to get at here is the last sentence on the page, because I was interested to see how you can look back at these two problems and complete this sentence. The majority answer that you submitted for this, to complete this sentence, was that the set of solutions of a boundary value problem is closed under addition and scalar multiplication only if, what did most of you write? I suppose you're only looking at your own paper, so I have to answer that question. What most of you wrote was something like, only if the solutions form a vector space or a subspace. And that is a very true statement, not the statement I'm looking for. So what I wrote on your paper, if you wrote that, is that you just gave me a circular definition. Because the definition of a subspace is something that's closed under addition and scalar multiplication. So yes, it's a true statement, but it's a tautology, right? We're not, what I was actually looking for, and again, this is me playing revisionist history. What I should have said is I should add a couple more words in here. The set of solutions is closed under addition and scalar multiplication only if the boundary value problem, so I'm looking for you to say something about the boundary value problem, not the qualities of its solutions, but something about the original problem. And I'm actually going to take the rare liberty of singling one person out because I'd like to hear more about what that person wrote on this, because I think it's the closest that we got on this part of the homework. Robert, would you mind sharing what you wrote on this last piece of the problem?
I personally wrote if the boundaries
Oh, you're looking at the front side. I'm talking about the back side.
Oh, wow. I wrote there's no lonely constants in the equation.
There's no lonely constants. I like that imagery. No lonely constants in the equation. Now, you said in the equation.
Yes.
Tell me about lonely constants. What were you keying in on there?
I'm trying to remember that.
Because I think I have a guess.
I don't remember.
Okay. So I'm going to try and read your mind. You didn't know that I was a psychic, but here I go. In the first part of the problem, the partial differential equation you had to work with looked like this. ytt equals a squared yxx plus 1. What's the lonely constant there? The plus 1. And you noticed if you plugged in y1 plus y2 into this partial differential equation in the first part of the problem, it was this plus 1 that screws you up. This is what made it so that y1 plus y2 was not a solution, even though y1 and y2 were. Because when we add them together, instead of getting a plus 1, we end up with a plus 2, right, when we add those together. So there's something about the partial differential equation having this extra additive constant that screws you over. That's what screws you over in the first part of the problem. But in the second part of the problem, something else also screws you over. And my hint is, don't just look at the equation, also think about the boundary conditions, the BCs. And try to make a statement that encompasses both of those things by paying attention to lonely, non-zero constants floating out there in the problem somewhere. So try and put that onto a firmer foundation, and I think you'll be on the right track for this last portion of the problem.